Hello everyone. Thanks to everyone for watching this video. My name is Qi Dang. I am an architect and engineer. Today's video is titled Yield Criteria, and it is going to introduce the failure series. I am going to give you an overview of what I am covering in today's video. First at all, it is a bit of background to the topic, and then focus on the Triska von Mises Mohr-Coulomb failure theory before wrapping up with conclusions. How can we predict when static failure will occur? What level do the stresses in the object need to reach for it to fail? First, we need to define what failure is. For ductile materials, failure is usually considered to occur at the onset of plastic deformation, and for brittle materials, it occurs at fracture. These points are easy to define for a uniaxial stress state, like a tensile test. They occur when the normal stress in the object reaches the yield strength of the material for ductile materials, and the ultimate strength for brittle materials. But for a more complex case of triaxial stress, predicting failure is much less straightforward. In fact, it's so difficult to predict that we don't have one universally applicable method. Instead, we have to predict failure by selecting the most suitable one of a range of different failure theories, each of which we know works relatively well under certain circumstances, based on experimentation. Because they fail in fundamentally different ways, failures which apply for ductile materials usually are not applicable for brittle materials, and vice versa. So, what does a failure theory do? It's quite simple. It allows us to predict failure of a material by comparing the stress state in the object while assessing with material properties that are easy to determine, like the yield or ultimate strength of the material, that we can obtain by performing a uniaxial. The stress state at a point can be described using the three principal stresses. So most failure theories are defined as a function of the principal stresses and the material strength. Now let's look at some better failure theories for ductile materials. Any good failure theory needs to be consistent with experimental observations we can make about how materials fail. There is one key observation that failure theories for ductile materials need to capture, which is the fact that hydrostatic stresses don't cause yielding in ductile materials. A ductile material under the action of equal principal stresses in three mutually perpendicular directions is subject to a hydrostatic pressure. The term hydrostatic is used because the material is subject to the same stresses as would occur if it were immersed in a fluid at a considerable depth. For a triaxial stress state, we can calculate the hydrostatic component as the average of the three principal stresses. The mechanism that causes yielding of ductile materials is shear deformation. Since there are no shear stresses for a state of hydrostatic stress, this component can be very large and still not contribute to yielding. Yielding is only caused by the stresses which cause shape distortion. These are called deviatoric stresses. The deviatoric component is calculated by subtracting the hydrostatic component from each of the principal stresses. The hydrostatic and the deviatoric components can be expressed in matrix form, like this. For triaxial stress, the principal strengths in the directions 1, 2, and 3 are expressed here. Young's modulus E and Poisson's ratio nu are the same for each direction. The strain energy stored per unit volume of the material is the sum of the strain energy in each direction. In terms of sigma 1, sigma 2, and sigma 3, the energy equation becomes this expression. For hydrostatic stress component, the strain in each direction is epsilon equal to sigma average over E times 1 minus 2 nu. The volume of the strand cube is epsilon cubic, because epsilon is small, so that this can be written approximately 3 times epsilon. Then the relationship between hydrostatic pressure and the volume strain is sigma average over 3 epsilon. The strain energy for producing only volume change is obtained by this equation. Then we can substitute sigma average expression into the strain energy equation and get the hydrostatic strain energy equation in terms of sigma 1, sigma 2, and sigma 3. For the deviatoric stress component, the strain energy of distortion is obtained as U minus UV equal to this expression. We know that at yielding during a tensile test in the maximum principal stress is equal to the yield strength of the material, and the two other principal stresses are equal 0. So we can calculate the distortion energy at yielding in a tensile test by plugging in the appropriate principal stress values. And by equating the distortion energy at yielding with the general equation for a triaxial stress state, and rearranging a bit, we get an equation that defines the von Mises failure criterion. This theory considers the difference between principal stresses, and so is independent of the hydrostatic stress. Now we know the three-dimensional stress system. Next, we will learn the failure theories. First, we introduce the Rankine failure theory. The Rankine failure theory is the maximum principal stress yield criterion. We can draw Mohr circle to represent the triaxial stress. Shifting Mohr circle horizontally represents an increase in the hydrostatic component, and increasing the radius of Mohr circle without changing the average stress represents an increase in the deviatoric component. The principal stress sigma 1 and sigma 3 cannot higher than yield stress sigma y. Next, we introduce the Triska failure theory. The Triska failure theory is the maximum shear stress yield criterion. It states that yielding occurs when the maximum shear stress is equal to the shear stress at yielding in a tensile test. We can also graphically use Mohr circle, like this. This theory is consistent with the observation that hydrostatic stresses don't affect yield. It doesn't care where Mohr circle is located on the horizontal axis. It is common to express this theory as a function of the principal stresses, instead of as a function of the shear stresses. We can see based on Mohr circle for a triaxial stress state that the maximum shear stress is equal to the radius of the outer circle, which is the difference between the maximum and minimum principal stresses divided by 2. Mohr circle for a uniaxial tensile test at yielding looks like this. The intermediate and the minimum principal stresses sigma 2 and sigma 3 are equal to 0, and the maximum principal stress sigma 1 is equal to the yield strength of the material. The shear stress at yielding is equal to half of the yield strength of the material. So we can rewrite our equation to obtain the standard formulation for the Triska theory. Let's look at the von Mises failure theory next, which is also called the maximum distortion energy theory. It states that yielding occurs when the maximum distortion energy in a material is equal to the distortion energy at yielding in a uniaxial tensile test. The distortion energy we introduced already. The strain energy equation in terms of sigma 1, sigma 2, and sigma 3 is shown here. For plane stress, sigma 3 is assumed as 0, so that the energy equation is reduced as this equation. In a situation of pure shear, yielding occurs when the shear stress is equal to the yield shear stress tau y. The Mohr circle for pure shear is shown here. From the geometry of the Mohr circle, we know sigma 1 is tau y, sigma 2 is negative tau y. Using the yield criterion, yield will occur in the pure shear when tau y equal to 0.577 sigma y. Failure of brittle materials is different to failure of ductile materials. Unlike ductile materials, brittle materials tend to have compressive strengths that are much larger than their tensile strengths. This needs to be captured in any failure theory for brittle materials. It also means that to assess failure of brittle materials, we need to know two separate ultimate strengths, for tension and for compression. Mohr-Coulomb theory is a failure theory often used for brittle materials. It considers failure to be sensitive to hydrostatic stresses and captures the difference between tensile and compressive ultimate strengths. The easiest way to define this theory is using Mohr circle. We start by drawing the Mohr circles corresponding to failure in the uniaxial tensile and compressive tests. By drawing lines tangent to both circles, we create a failure envelope. Mohr-Coulomb theory states that a material will fail for a stress state with a Mohr circle that reaches this envelope. From conclusions, what we learned? A yield criterion is a hypothesis defining the limit elasticity in a material and the onset of plastic deformation under any possible combination of stresses. Von Mises yield criterion considers that the yielding of a ductile materials begins. Mohr-Coulomb yield criterion is a mathematical model describing the response of brittle materials. Okay, thanks to everyone for watching my video today, and I do hope you found the video informative and that you learned some things from it. If you do have any questions, then you can write comments and messages. I am happy to answer any questions. Thanks for your watching.